Welcome to this lecture series in real analysis. We have previously discussed what can we say about the sum and the scalings of convergent series, and the results that we obtained were pretty simple. If we have two convergent series, summation an and summation bn, then we defined their sum as the following. And what we found was that if this is a convergent series which limits to little a, and this is a convergent series limiting to little b, then this is also a convergent series limiting to a plus b. And a similar simple result about scalings. Naturally, we would like also to ask the question, what can we say about the product of two given convergent series? Turns out the answer here is not as nice or requires some more hypothesis than just the convergence of the two. So it is something that we definitely need to discuss. So this lecture will be dedicated to it. And maybe in future we will use this. But for now, this is just think of this as a standalone necessary lecture. All right. Here are some problems for practice. At the end of this exercise set, you will also be able to prove the convergence of this interesting infinite series. Okay. So we'll first need to address a technical lemma. It will not make much sense, but it's a fun exercise, if you will. So we start with an absolutely convergent series and a sequence which is a null sequence. It converges to 0. With these two things, we define this funny looking term gamma n, or funny looking sequence gamma n as n being taken from so the starting index here is 0, so gamma 0 is also defined. So here also the starting index is 0. Okay, so we define gamma 0, gamma 1 and so on via this formula, funny looking formula. And our conclusion that we want to prove is that gamma n is also a null sequence. Okay, so it's an exercise in some sense. Why do we need to prove such a thing is unclear, but let's just run with it. In fact, I encourage you to pause the video and find your own proof. That will be better than looking at what I'm going to do. Okay, so define A as the sum. Define this because the series is absolutely convergent. This is a meaningful real number, and that is what we declare as A. And if little a is 0, then nothing to do. Then what happens? Then that means that each an is 0. If each an is 0, then gamma n is the constant sequence 0, and hence this conclusion is trivial. So if a is 0, then we are done. So we may assume that a is non-zero and hence strictly positive. So assume a is strictly positive. Okay, and let epsilon greater than 0. Then there is n such that whenever little n is greater than capital N, we have this is less than epsilon by 2a. Now, why this thing is chosen this way will be clear in the course of the proof. When you are writing a proof, this is not how you start. You figure out these things as needed. So perhaps I should have left it blank. But anyway, I don't want to spend too much time on this proof. So if little n is greater than n, then what is gamma n, or rather absolute value of gamma n? By definition, this is the absolute value of the following. Right? Which we will write in two parts. The first part will run from 0 to capital N. And the second part will run on the remaining indices. because little n is greater than capital N, this is a meaningful partition. By triangle inequality, this is at most. This is at most that thing. And further application of triangle inequality. This. Right? So what did we do here? We just applied triangle inequality to break it apart into individual terms. Okay. Now, by the choice of capital N, we can further estimate this as follows. Right? Because each of these terms is at most that by the choice of capital N. Now this can be further estimated as follows. Right? Here there were a bunch of terms. We are just adding more terms. So since each of the terms are non-negative, this is perfectly fine. And these two things cancel out because what is this infinite sum? This is just capital A. Sorry, this is just little a. So they cancel out and we are left with, this is equal to that much. Okay, so what we see from the above working is that this is at most this funny term for all little n exceeding capital N. Okay. But since this is absolutely convergent, we have that this is the case. Right? Any convergent series has this property that the nth term of the sequence of the series goes to 0 as n approaches infinity. So this being an absolutely convergent series is definitely a convergent series, and hence the nth term being an converges to 0. And now look at this. If little n is pretty large, each of them are small. Right? If little n is large enough, much larger than capital N, then each of these terms are small. Correct? So what we get is this thing can be made as small as you want, because there are only finitely many of the betas that you're adding. Fixed, this capital N is a fixed number, some fixed entity. And if you choose n large enough, this can be made as small as you want, so on, so on. This can be made as small as you want. And there are only capital N many terms, so you can make this as small as you want. I don't want to write all of that. So from here you conclude that gamma n or mod gamma n is less than epsilon by 2 plus epsilon by 2 ultimately. And that's it. That shows that gamma n converges to 0. So that's the proof of this lemma. And now we will use this lemma. We will use this lemma to get to the main point of this lecture. So we again have an absolutely convergent series and another convergent series. And we will define a sequence which we will explain. So this starts again, this also starts with a 0. So how do we define it? In this funny fashion. C0 is A0 times B0. C1 is A1 times B0, A0 times B1, and add them. C2 is some of these three things. And the nth term in this sequence Cn is summation of ai times bj, where I and j are indices between the range 0 to n, but with the property that they add up to n. So this is a general way of expressing the nth term. Here they were special instances of it. Now this may already seem like a very funny thing to define, but here is the motivation. Suppose you were trying to find the product of the following. These are just two polynomials. What would we do? Like in high school, what do? We find that the product is a0 b0 plus a0 b1 plus a1 b0 times x plus a2 b1 plus a1 b1 plus a0 b2 times x square, and there are more terms. Right, so that is just when you are producing two polynomials of degree 2, but here, what are we trying to do? We are trying to product infinitely many terms with infinitely many terms. So this will go on up to infinity, and same for this. And that's kind of the motivation behind these numbers. We are just extracting out the coefficients. So that is some motivation for defining the product like this. It is a fairly decent way to define product. Of course, you could have defined the product in some other way, but that won't be useful. Anyway, so this is how we define the product of the two series. So the product of the two series is this series where the nth term is defined via this formula. And what we are proving, what we are going to prove is that if one of these two is absolutely convergent, in the enunciation of the theorem I have mentioned the first one to be absolutely convergent. Doesn't matter, we just need at least one of them to be absolutely convergent, and then we can show that the producted series is also convergent. If both are absolutely convergent, great, but it is not enough to just have both being convergent. We need absolute convergence of at least one of them. Further, the producted series sums to the product of the two. Naturally, this is what we would want. Otherwise, why would we even be defining the product? So the limit or the sum, this thing, the producted series, since it is a convergent series, we can think of this thing as a number now. This number is nothing but the product of the limits of the two series or the sums of the two series. Okay, so this is what we need to prove. Alright, so we will develop some notation, and at some point we will invoke the lemma that we proved in the previous slide. So define capital AN as the nth partial sum and capital BN as the nth partial sum of the other series. Define capital A as the limit of these partial sums, which exists because of convergence of the first series, and capital B as the limit of the capital BNs. Okay, so just another way of writing capital A would have been this. We could have just written it like this, and similarly for that. Okay, define Cn or capital Cn as the nth partial sum of the small cn's, and write capital C to mean the product of A and B. What we want to show that C is the limit of the capital Cn's. Right? Okay. So now we start this project. So capital Cn is what? Capital Cn is, by definition, this thing, the nth partial sum, which by definition is something is wrong. Yeah, that's what it is. which can be rewritten as follows. So this is A0 times that plus A1 times that plus ... this thing. Right, I just did some basic algebra here. A0 times B0, then you have A0 times B1, then you have A0 times Bn, and so on. Okay, but by definition of the capital Bn's, this is A0 times capital Bn plus A1 times this plus... yeah, we have that. All right, and let beta n as Bn minus B. This will be convenient, and note that beta n is a null sequence. This is nothing because what is the limit of Bn's? It is capital B, by definition of capital B. So we have this. Of course, this also means that Bn is B plus beta n. Okay, so therefore Cn is A0 B plus beta n plus A1 B plus beta n minus 1 plus ... an B plus beta 0. We didn't do anything, we just wrote B, capital Bn as this and this as that, and so on. All right, so this can be written as follows. Right, just basic algebra. And let us call this gamma n. Okay, so this thing can be written as that thing. But by the previous lemma, the technical lemma, this converges to 0 because beta n's converge to 0, and this series is an absolutely convergent series. So that's it. I mean, that was the previous technical lemma that shows that gamma n converges to 0. This of course converges to AB, and that's it. So therefore, by the previous lemma, this converges to AB as n approaches infinity, and that finishes this proof. So that's all that I want to say. All of this I believe is, or I admit, seems quite technical, but at some point I want to use this perhaps when we will be discussing sequence and series of functions. Then this may turn out to be very useful. As of now, it does seem to be a little bit isolated from the rest of the material. Anyway, with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.